Welcome. In this video, where we're going to implement the great 3D Gaussian splatting paper from scratch using PyTorch-Only. Okay, so no C++, no CUDA, just PyTorch. We're going to dive into the code in a bit, but yeah, you can see the beginning of the code. These are the only 4 libraries we're going to use. So PyTorch, NumPy on Pillow to save the generated images, but you can see that we're not using any external libraries for everything related to 3D. And we're not going to use any C++ or CUDA complexity. Everything is just PyTorch. Okay, so at the end of this video, you will really understand all the details of the Gaussian splatting, so the splatting process. Yeah, you will know all the details because we're going to implement everything from scratch. These are the results you can expect by the end of this video. So I have a link where you can download pre-trained Gaussians for the 4 indoor scenes of the MIPNERV 360 dataset. So the kitchen scene, the bonsai scene, the room scene, or the counter scene. And basically what we're going to do is to generate a camera path around the object, and rotate around it, and make videos like the one on the right. So this video is only for the rendering, for the splatting of the Gaussians. It's not for the training. I will maybe make further video later on training of the Gaussians, but for now only focus on the rendering. The code is open source. I will give you the link in the description. If you find the code useful, please leave a star on this GitHub repo so that other people can discover it. And yeah, by the end of this video, you will have a code like this one, so you can see it's only a few hundred lines of code, and it implements the full splatting approach of the Gaussian splatting paper. Okay. These are pre-trained Gaussians after 7K training iterations. And if you compare the metrics of this code on the code from the paper, metrics are alike. So this implementation is of course a bit slower because it's in PyTorch, but in terms of quality, it's on par with the paper. Okay, let's dive into the implementation. So as in NERV, what we want to do is to model the fact that the color of a 3D position is dependent on the viewing direction. That's why each Gaussian do not store like a RGB value, a color value, but what we need to store, it's a function so that we can modulate the color value of each Gaussian as a function of the viewing direction, okay? And we do that with spherical harmonics. Here in this video, I'm mainly focusing on the implementation, but all this code is coming from my course on 3D Gaussian splatting. I will put the link in the description if you want to move further, understand things a bit in more details. But basically, I explain my code where those coefficients are coming from. Yeah, I explain all the maths behind it and how you can derive them. So basically, here we're going to create the function that, given a viewing direction and given the spherical harmonics coefficients that have been learned per Gaussian, we're going to return the color for that Gaussian given the viewing direction. Okay. So basically here we're going to use a spherical harmonics of degree 3. So that means that for each channel, so we have 3 channels, RGB, and for each of those channels we have 16 components. Because we're using spherical harmonics of degree 3. So basically what we do, we pack those parameters that are learned per Gaussian, FDC and FREST, and we just create a SH variable and pack those values in that SH tensor. Then we compute the view direction. So basically we have the points. Basically these are the 3D locations of the Gaussians. And we compute the vector from, well, between the camera and the Gaussian. So that gives us the viewing direction for each Gaussian. We normalize the viewing direction, and then we get the XYZ component. What we do, we create some intermediate variables so that our code later will be easier to read. And basically now we can create the basis for the spherical harmonics. So you can really think about spherical harmonics as like some kind of Fourier basis on the sphere. Yeah, they allow to model function on the sphere. So basically we create those bases. Those bases, basically this is just maths, okay? So basically here we just encode the maths from the theory. And then what we do, we are going to weight each of those bases with the learned coefficients, so SH. Yeah, those coefficients, again, they are FDC and FREST that are learned per Gaussian. So basically we can weight Y with those learned coefficients and use a sigmoid so that the color is between 0 and 1, okay? I have made other videos on NERF on related to plane oxel or to plane 3. These papers also use spherical harmonics with NERF. Maybe you might be interested in those papers. Okay, so maybe that was a bit complex to start, but again, that's just a way. For each Gaussian, we store a function that allows us to be evaluated. We evaluate it based on a viewing direction, so basically based on x, y, z. And basically this function takes x, y, z as input and gives us the color of the Gaussians. Now that this is done, we can implement easier functions. First with the project points that will be used for the splatting. So basically we're going to project each Gaussian from 3D to the image plane, okay? So basically here we're just implementing the perspective projection of the pinhole camera. So basically I'm receiving the camera to world matrix as input. From it, I'm computing the world to camera matrix, okay? So we just, it's not a matrix inversion, but in a way we invert the camera to world matrix to get the world to camera matrix. And then we can basically do a matrix multiplication so that we transform the Gaussian coordinates, so PC, the 3D means of the Gaussians. We project them into the camera coordinate system, and then we can do the perspective projection with the equation on line 74. All that is explained in detail in my course, but again here we do not focus on the equations, we mainly focus on the implementation. Okay, so now we can implement a function that will be used later. Basically, it just allows us to do an inversion of a matrix. So basically, we take a batch of matrices, so M. So the shape is N, the batch size, comma 2, comma 2. And then we compute the inverse of those matrices. And yeah, so basically the code is pretty simple. We just implement the inversion mathematically. Okay, we just compute it analytically. And then we derive the inverse of the matrix. Okay, so basically for the Gaussian splatting, basically each, well, as the name suggests, the scene representation are Gaussians. So each Gaussian is parameterized with its mean, its position in 3D space on its covariance matrix. But basically, because the covariance matrix needs to have some properties to be valid, to have a physical meaning, we do not directly learn or optimize the covariance matrix, but we do a specific parametrization, okay? So that's how the Gaussian is parameterized, while all the covariance of the Gaussian is parameterized with a scale matrix and with a rotation matrix. So basically these are the components that are learned, okay? So that we can do an unconstrained optimization, and then from those unconstrained variables, build the covariance matrix. So basically here we just build, basically we just implement equation 6, building the covariance matrix from the scale on rotation matrices. What we do, because the scale should always be greater than 0, instead of modeling the scale directly, we model the log of the scale, because the log can have any value, and then we take the exponential so that we get the scale. The rotation matrix, it's modeled by a quaternion. And basically, yeah, the quaternion, it's a vector with 4 values in it. The viewing direction on a value W, which means by how much we rotate around that vector, around that direction. On this vector should be normalized, but again, we first, for gradient optimization, we learn the unnormalized vector, and then we normalize it, okay? So scale rho and Q rho are the Gaussian parameters, and then from there we do a reparametrization, and then we can build the covariance matrix by implementing equation 6. And you can see that we need to convert the quaternion to a rotation matrix. So we're going to do that in the next function. So basically a rotation matrix, it's a 3 by 3 or a 4 by 4 matrix, and basically it's over-parameterized. If you compute the well, basically there's some redundant value in the rotation matrix, so you could just summarize it with 4 values, and that's what the quaternion is doing. And here basically we go from the quaternion to the rotation matrix. These are very well-known equations in graphics. Again, here I'm not going to discuss too much about the equations. Okay, so basically that's just how you go from a quaternion with the XYZ component, so the direction, W the amount by how much you rotate around that direction, and basically you can convert that into rotation matrix. Okay, so we're almost ready to implement the interesting part, so the splatting of the Gaussians. And you can see that you already know that our final code will be about 300 lines of code, but you can see that we already have just used 100 lines of code for the helper functions. So basically the splatting will be very, in a way it will be very easy. It will be maybe 200 or even less lines of code. So basically, we want the ability to rasterize or to splat, to generate an image with any resolution chosen by the user. On basically, because when we do this projection, so project points, this projection depends on the camera parameters, on mainly the intrinsic parameters. So these are parameters of the camera, such as the focal length. And therefore, if I want to generate the image at a lower resolution and get the exact same image, I need to adapt my parameters. So basically here, the scale intrinsic parameters, while the scale intrinsic function take as input the initial width on 8 of the image, compare it to the width on the 8 that the users want to use, and then it will scale the camera parameters accordingly. Okay, and basically the equations are pretty straightforward. You just scale everything by the ratio between the new width versus the old width, and same for the height. And now we can finally implement the interesting function, the rendering function, the splatting function. So we take as input all our 3D Gaussian parameters, so the position, so the 3D mean, the color for the Gaussian that we've pre-computed with the evaluate SCH function based on the camera roll matrix, based on the viewing direction. Then we take the opacity of the Gaussian on the covariance that we've built with the build sigma from params function. There are a few other, well, we also take as input the camera parameters. So it's camera roll matrix, so the position of the camera, its rotation, the height and the width with which we want to do the final image height and width, and also the focal length on the center of the image for this specific resolution. And there are a few other extra hyperparameters. Most of them are described in the paper. For example, if you go in the supplement, they describe some parameters for numerical stability. For example, okay, here they describe a few parameters. For example, alpha max or alpha cutoff, but we are going to discuss that in a bit. Okay, so what we can start is basically we have the Gaussians in 3D space, so we can project them in 2D space. We can project them to the image plane with this project points function. Based on where the camera is, not all the Gaussians will make it to the image plane. Some will be behind the camera. Some Gaussians will be outside of the screen. So basically, after we've projected the points to the image plane, we check, we make sure that the Gaussians are in that the Gaussians are on the screen, and we only keep the Gaussians that are on the screen. So that's what those in-guard parameters are doing. Okay, so we only keep we only keep components or Gaussian attributes for the Gaussians that make it to the screen. We create an index value. The index value will allow us to track the Gaussians. Basically, it gives us an index for all Gaussians that make it to the screen. But we're going to use that later. Okay, so now that we've projected the Gaussian means, so the location to the image plane, so we know where each Gaussian is, we also need to project the covariance matrix. So we need to go from a covariance matrix in 3D space to a covariance matrix in 2D space. This is equation 5. So basically we need to go from sigma to sigma prime. We need to go from the world space to the 2D space. So basically it's just we compute, well, it's a matrix multiplication. between the viewing transformation on J, the Jacobian of the perspective projection. So basically here we retrieve W. So W is the world to camera matrix. So we create the world to camera matrix from the camera to world matrix, and then we create the Jacobian of the perspective projection. Okay, so when this is done, we can implement equation 5 directly. So basically I've just splitted it in 2 lines of code for the for making it readable, but basically it's just a straightforward implementation of this equation, the Jacobian multiplied by the by W multiplied by the covariance in 3D space, and so on and so forth. Then what we can do for numerical stability, the covariance matrix, it's only valid if it meets some properties. So first it should be symmetric. So what we do, we rewrite, basically there might be some noise in the projection, due to numerical instabilities. What we do, we rewrite the sigma camera to enforce symmetry. We just use algebra so that we make sure that the covariance is symmetric. And then this is maybe extra cautiousness. Maybe it's not really needed, but we rebuild the covariance matrix to make sure that it's positive definite, okay? Because it only has a physical meaning if it's positive definite. What we do, we compute the eigenvalues on the eigenvectors of the matrix, and then we rebuild it from its eigenvalues on eigenvectors, again, to make sure that it's positive definite. Okay, when this is done, we can sort the Gaussians by depth, because later we want to do alpha compositing, and therefore for doing that we need to make sure that they are ordered by depth. We are almost ready to do to implement the volumetric rendering equation. So this is equation, it should be equation 2 or equation 3. Yeah, basically equation 2 and equation 3. Volumetric rendering. If you are familiar with NeRF, I've done a lot of videos on NeRF. You are familiar with those equations. Before doing that, we need to split the screen into tiles. So basically that's what the Gaussian splatting approach does. It splits the screen into tiles for efficient parallelization. So they parallelize over pixels rather than parallelizing over the number of Gaussians. So that's described very well in the Pulsar paper. That's a paper that is often overlooked, but that's a very important paper in this research community. It was a kind of pioneer work to Gaussian splatting. And they explain that. Basically, you can do either parallelize over Gaussians or parallelize over tiles. They explain a bit the pros and cons of each method. But basically here what we do, we parallelize over pixels, so we create tiles and iterate over each tile one by one. So basically here what we are going to do, we are going to check which tiles each Gaussian intersect, and then later we are going to iterate tile per tile, and for each tile we are going to implement those volumetric rendering equations. Okay, so basically we compute the radius of each Gaussian. So Gaussian, of course, these are continuous. They have a continuous density. Well, they have a continuous PDF, so that defined everywhere. But basically, we compute the radius, so that basically we will compute the Gaussian that have a 99% probability intersection. Well, we compute the tiles that have a 99% probability intersection with the Gaussians. So basically, we compute the radius accordingly. And then we compute the AABB box. So basically, we compute the coordinate of the bounding box around each Gaussian. So this is this Umin, Umax, Vmin, Vmax values. These are the coordinates of the top left corner on the bottom right corner of the rectangle around the Gaussian. Then we check which Gaussians are on screen. So basically, we make sure, based on those AABB box, there are some Gaussians that are out of the screen, so we're going to remove them. And then basically, here what we do, we compute the tile index for each bounding box. Basically, we convert pixel coordinates, so Umin, Umax, Vmin, Vmax are in pixel coordinate. We convert that into tile index, so we divide by the tile size, which by default is 16 pixels. Then we can compute for each Gaussian the number of tiles it intersects. Here we are going to compute. We're going to use that just after, but basically we compute the maximum number of tiles intersected. So overall, if we check all Gaussians, what is the maximum number of tiles intersected? And then basically now what we can do, we can create, let's wait a bit. Basically we can create flat tile U, flat tile V. Maybe before explaining what this is, let me generate the next part of the code. So basically what we're going to do, we are going to create three tensors. Well, these are three related tensors. So basically here we have Gaussian IDs. So basically that tells me that Gaussian 0 is intersecting the tile at coordinate 0, 0. Okay? So the U and V coordinate of Gaussian 0, it's 0, 0. And then we see that the Gaussian 0, it's appearing again. So Gaussian 0, it's intersecting with tile 0, 1. And then again, Gaussian 0 is intersecting with 1, 0. Again, Gaussian 0 is intersecting with tile 1, 1. And then now we move on to the second Gaussian. So the Gaussian with ID 1 is intersecting the tile 2, 2, and so on and so forth. And basically on line 234, what we do, we combine flat tile U and flat tile V in a single variable. Basically, we instead of using a 2D index, we create a single 1D index. Okay, we kind of flatten the 2D image into 1D array, and we use a 1D index. Okay, now what we're going to do, we're going to do a lexicographic sort. So basically, what we have our Gaussians are already sorted by depth, but what we want to do, we want to iterate tile per tile. So we need to do two things. We need to sort the Gaussians by tile, and then within a tile, we need to sort them per depth. So basically, that's what they explain in the paper. That's the radix sort with two keys. In our case, the first key is the tile ID. The second key is the depth. And basically, we are going first to sort by the first key. And then if two Gaussians, if two values have the same first key, so the first key is the tile index. If two Gaussians have the same tile index, then we are going to sort by depth. So that within a tile, Gaussians are sorted per depth. So in NumPy, there is a function to do that, to do a lexicographic sort. In GPU programming, you can do that with a radix sort, but here we need to do it ourselves because there is no lexicographic sort in PyTorch. So basically, we do what we did with flat tile ID. We combine the two keys into a single key with this equation. Basically, that's a common equation when you want to go from a 2D index to a 1D index. We combine that into a single value, and then we sort that value, comp for composing. And then basically, once we've done the sorting, we retrieve the two values. So for example, the tile IDs by doing a division by this value m. Given this equation, if I know m, I can retrieve each value by using the modulo on the division. Okay, so once this is done, so again, that's equivalent to the radix sort in the paper. Now that it's done, we need to know, basically, again, we have two big vectors. One is tile IDs, okay, that tells me for each Gaussian the tile that it intersects. And we also have Gaussian IDs, so we have two, they are related. So first, Gaussian IDs tells me the Gaussian IDs, and the tile IDs tells me the tile IDs, and they are related, they have the same length. And basically now I need to iterate over them. I need to iterate tile 0, then tile 1, then tile 2. So basically I need to know, basically you can have a look at this comment, but I need to know which are the indices I should consider, okay? So basically, if I want to have a look at tile 0, here I need to have a look at the first three values. So basically the start is index 0, and the end is index 3. And basically this is what the start and the end index means. Maybe that will become clearer in a moment. Before moving on, what we need, for example, if we go back to the Gaussian Splatting paper, when I'm computing the Gaussian PDF, I need to compute the inverse of the covariance matrix. So I think, yeah, basically equation 4. To evaluate g of x, I will need the inverse of the covariance matrix. So I'm already pre-computing the inverse of the covariance matrix using this inv 2x2 function that we've created before. And now I'm ready to iterate over tiles, so basically I can create the final image, and we are going to feed it tile per tile. So basically you can see that now we iterate over the tile indices, and we also take S0 and S1 to know the indices related to those tiles. Okay, so again, if I'm, for example, if you look at tile 1, I need to know that it's between index 3 and index 4. And basically that allows me to retrieve the Gaussian IDs at those locations. So what we can do, we have again the tile ID. Now what we need to know, basically to compute again equation 4, I need x here, it's basically it's an abuse of notation. Basically x, it should be called delta x. That's the difference between the center of the Gaussian and the pixel coordinate. So basically I need to know the pixel coordinate for all pixels in the tile. So first I'm computing, I'm converting the tile indices into pixel coordinates. So basically using the mesh grid function, here I'm computing the pixel indices, pxu, pxv is the pixel coordinates for each pixel in the tile. Okay, so now that I know my Gaussian IDs, I can retrieve the Gaussian attributes for each Gaussian. So it's its coordinates, while the coordinates of the projected mean, which is now in 2D, so the u and v coordinates, the color of the Gaussian, its opacity, and its inverse covariance, so that I can compute the volumetric rendering equation. So du dx, well, du dv, this is what we just mentioned. So basically we are computing x, basically the distance, well, yeah, the distance between the pixel coordinates on the center of the Gaussian. On basically what I'm computing here in line 288. So q, basically it's just, I'm just analytically writing this term. Well, not I'm not taking the coefficient into account. I'm just computing this. I could write it just with matrix multiplications in PyTorch, but doing it directly with the analytical formula is faster. Okay, so now what I can compute is g of x. So basically g of x, it's this full term, so equation 4. And basically we only consider Gaussians when they if q is smaller or equal than a chi-square clip, that by default is equal to 921. And basically a value of 921 means that we if q is smaller than 921, 921 can be seen as a distance threshold, and if we are below 921, we are within the 99% probability. So okay, we only consider Gaussians. Well, we only consider a pixel if it intersects the Gaussian with a probability higher than 99%. So then we can compute alpha. So basically, as they describe in a paper, the alpha value it's g of x. So basically, this PDF times the per Gaussian opacity, that is a learned coefficient. So basically, each Gaussian is a parameter, a Gaussian opacity that is fixed. And then we also evaluate the PDF of the Gaussian. So the further away we go from the mean of the Gaussian, the lower the opacity. In NRF, neural radiance field, alpha is given directly by the neural network. Now that we have alpha, we can compute 1 minus alpha. That will be used later to do compute the transmittance. Basically talking about the transmittance, we can compute it directly. Again, if you've seen my video on NERV, you know about that. From now on, it's only volumetric rendering. So basically now that we've computed the weight, basically if we go back equation 2 on equation 4, well, equation 2 on equation 3, once we've computed basically we can compute directly the color. The color, it's the weight. Basically the weight, it's the transmittance times the alpha times the color. So basically we can compute that directly. On that gives us the color of the pixels for this style. And basically that's it. That was the implementation of the splatting approach. So basically there is a lot of software engineering, for example, for computing the tiles on the tile indices. But all that aside, once you are in the for loop, it's just like volumetric rendering as you know it is in NERV. Okay, and now we can put everything together. So we can implement the main function. So let's start by loading the 3D Gaussian splatting parameters that have been learned. You can see here this is for the kitchen scene, trained after 7K iterations. But you will have access to other scenes, and you can, for example, change the names. For example, you can load the bonsai scene or other scenes. Then we are going to load the camera parameters that are extracted from CallMap. And I've pre-computed a camera camera path that will rotate around the object, so that we can generate a 360 views around the object, and then make those kind of videos. Again, all the details on how to generate those are described in my course. Okay, so now that we've loaded the parameters, we can build Sigma. So Sigma, we need only to build it once. Basically, what we could do instead of saving Q on scale, we could just save Sigma, because Q on the scale that just needed for training. Once training is done, we can just compute Sigma and just use Sigma from now on. Okay, we don't need to recompute Sigma for every viewing direction or at each inference step. We could just compute Sigma only once. Okay, well, let's move on maybe. So what we're going to do now is to iterate over each camera tool matrix. Okay, so we're going to do this 360 video. So we're going to iterate over each camera. We're creating creating an orbit, and we're iterating over each camera. And basically, my point is that, well, what I wanted to say is that Sigma, we computed it only once, but the color that we're going to implement in a bit, okay, line 334, the color, we need to recompute it every time we change the camera tool matrix, okay? Because the color is a function of the viewing direction, so it's a function of the camera tool matrix. So every time we have a new camera tool matrix, we need to recompute the color to call this evaluate sh function. But this function is really fast. And then when we've done that, we can call the render function to do the splatting approach, and then we can save the image. Okay, that's it for this video. I really hope it was helpful to you. If it was, please leave a thumbs up, comment to help this video get traction. If this video does well, I will create more content related to Gaussian splatting. I might add a video on the training code. I will modify this code to implement follow-up papers on Gaussian splatting, for example, to make the rendering faster. So yeah, please help me to make this video get some reach. Comment it, leave a thumbs up, and subscribe for more content related to Gaussian splatting. As a reminder, if you want to dive deeper into Gaussian splatting, I have a 16-hour course on it, and I will put the link in the description.